The stereochemistry of an alkene can also have an impact on its general stability. So let's take a look at this cis and this trans alkene. If we were to burn these, we would get different amounts of energy from them. For example, if we burn our trans alkene, we would get minus 2682 kilojoules per mole of energy out. If we burnt our cis alkene, it would be 2686. So what's the difference here? This, we would be getting out an extra 4 kilojoules per mole, which means that this molecule, the trans molecule, is higher energy to begin with. We can attribute this to the steric strain associated. Just like if we had an eclipsed conformation with an alkane in a cis configuration will actually be higher in energy. We can actually draw a modified Newman projection of these to show that. So if we take a look at our trans alkene, our front carbon, let's identify the front carbon as being this one. We're looking straight down the middle of that axis. We're going to have a methyl group coming off to the right. We're also going to have a hydrogen coming off to the left. We're going to have p orbitals coming up from the top and the bottom. If now we draw our back carbon, the p orbitals are in line, so I'm just going to shift them over a little bit. There's our pi bond. The hydrogen is going to be over here, and the methyl group will be over here. So in terms of being an eclipsed conformation, notice the methyl group and the hydrogen are eclipsed, but the two methyl groups are on opposite faces. If we were to draw a similar projection for the cis alkene, again, we've got our double bond here, a methyl group coming off to the right as we look at the first carbon, which is here. We have in the back carbon our double bond. We have the methyl groups on the same face. So this steric interaction, this bulk, will actually make this conformation or this configuration less stable, and if we burn it, we're going to get more energy out. Alkane stability also depends on the degree of substitution. This will actually trump having a cis or trans configuration. So in this case, we have a mono-substituted alkene. Let's draw this in a three-dimensional space. So we have our p orbitals here. We have a methyl group coming out towards us, which means we're going to have a hydrogen here. We've got our hydrogens back here. These are also hydrogens. In this case, because we've got an overlap of electron density between the carbon and the hydrogen here to make that sigma bond, we actually have hyperconjugation. So some of the CH bond electron density is distributed into our alkene. You should remember that hyperconjugation is stabilizing. If we have a di-substituted alkene, this is actually increased. So we've got our p orbitals here. The alkenes are going in opposite faces. Let's draw our hydrogens. And again, if we have an orbital here and we have an orbital here, what can happen is that this can donate some electron density into the double bond, and the same thing here. So in the case of our di-substituted alkene, we actually have two sources of hyperconjugation. So this will be more stable than the mono-substituted alkene. If we move it up to a tri-substituted alkene, even though there's this additional cis clash here, because there's an extra source of hyperconjugation, this will be more stabilized. Finally, if we have a tetra-substituted alkene, it will have four sources of hyperconjugation, and it will be the most stable form of the alkene.